Welcome back to another video. In this video, we will learn about regression and logistic modeling, a comprehensive guide. So let's get started. Welcome to our exploration of regression and logistic modeling. Today we will delve into the world of statistical modeling, uncovering its power and applications in data analysis. We will explore how regression models estimate relationships between variables and how logistic models predict categorical outcomes. Simple linear regression, exploring relationships. Let us understand what is simple linear regression. Simple linear regression analyzes the relationships between two variables, one dependent and one independent, seeking to establish a linear equation that best fits the data. This model helps us to understand how changes in the independent variable affect the dependent variable. So let us take an example. Imagine we want to predict house prices based on their size. Simple linear regression could help us found the relationship between square footage and price, providing a prediction equation for estimating house values. Multiple linear regression, extending the scope. Multiple predictors. Multiple linear regression allows us to model the relationship between a dependent variable and multiple independent variables. This enables us to capture more complex relationships, accounting for a wider range of factors that influence the outcome. Second is predictive power. Imagine predicting customer satisfaction based on factors like product quality, price, and customer service. Multiple linear regression can incorporate these factors to provide a more comprehensive model for predictive satisfactions. Data insights. Beyond predictions, multiple linear regression helps us to understand the individual contribution of each predictor variables to the outcome. This provides valuable insights for informed decision making. Regression diagnostics, assessing model assumptions. It consists of four methods: linearity, homoscedasticity, independence, and normality. First, we understand what is linearity. Linearity, verifying the linearity assumptions, ensures a linear relationship between the dependent variable and the independent variables. Residual plots helps us identify deviations from linearity, suggesting potential adjustment to the model. Then comes homoscedasticity. Homoscedasticity implies constant variance in the errors across the range of predicted values. Examining residual plots for patterns and uneven spreads indicates potential issues with these assumptions. Independence. The independence assumption ensures that the errors are not correlated with each other. Time series data may exhibit autocorrelation, requiring adjustment to the model. Then comes normality. The normality assumptions suggest that the errors follow a normal distribution. QQ plots help visual assess normality and guide decisions on the model adjustment or alternative approaches. These four methods are comes under the regression diagnostic. Regression model evaluation. Key metrics. There are three methods of model evaluations. First is R square. R squared measures the proportion of variance in the dependent variable explained by the model. A higher R squared indicates a better fit but doesn't guarantee a good model. Then second is RMSE. Root mean squared error, a measure of the average difference between the predicted and actual values. Lower RMC indicates better prediction accuracy. Then third is MAE, mean absolute error, a measure of the average absolute difference between the predicted and actual values. Lower MAE indicates better prediction accuracy, more robust to outliers. Stepwise regression, automating feature selection. First is forward selection. Starting with no variables, the algorithm adds variables one by one, selecting the one that improves the model fit the most at each step. This continues until adding further variables does not significantly improve the model. Then second is backward elimination. Starting with all variables, the algorithm removes variables one by one, removing the one that contributes least to the model fit at each step. This continues until removing further variables significantly worsens the model fit. Then third is stepwise selection, a combination of forward and backward selection, in iteratively adding and removing variables based on statistical significance. This approach aims to identify the optimal set of predictions for this model. These are the stepwise regression, automatic feature selection, logistic regression modeling, predicting categorical outcomes, predicting categories. Unlike linear regression that predicts continuous outcomes, logistic regression predicts categorical outcomes, such as whether a customer will click on an ad yes or no, or whether a loan will default yes or no. Sigmoid function. The sigmoid function transforms a linear combination of predictor variables into a probability rank ranging from 0 to 1, providing a continuous probability estimate for the categorical items. Applications. Logistic regression is widely used in areas such as marketing, finance, healthcare, and social sciences for making prediction about categorical outcomes based on relevant factors. Logistic regression for binary outcomes. A practical example. Predicting loan default. Imagine we have a dataset with information about borrowers, including age, income, credit score, and whether they defaulted on a loan, yes or no. Logistic regression can help us predict the probability of a borrower defaulting based on the characteristics. Model interpretation. The model coefficient reveals the relationship between each predictor variables and the probability of default. A positive coefficient means a higher value of the predictor increases the probability of default, while a negative coefficient indicates the opposite. Interpreting logistic regression coefficients. Odd ratios. Logistic regression coefficients are expressed in terms of odd ratios, which represents the change in odd of the outcomes for one unit. Increase in the predictor variable, for example, an odds ratio of 2 means the odds of the outcome double for every 1 unit. Increase in the predictor. Sign of the coefficient. The sign of the coefficient tell us the direction of the relationship. A positive coefficient indicates a positive relationships where an increase in the predictor increases the probability of the outcome and vice versa for a negative coefficient. Third is magnitude of the coefficient. The magnitude of the coefficient indicates the strength of the relationships. A larger magnitude implies a stronger relationships between the predictor variables and the outcomes. Poisson regression for count data analyzing event. Poisson regression is designed to analyze count data representing the number of events that occur within a specific time interval or space. This model is particularly useful when the dependent variable is a count, such as the number of websites, customers' complaints, or accidents. So that's all for today's video. Thank you.